We can start. So good morning, everyone. It's a pleasure to introduce today's speaker, Giulio Fabbian. Giulio did his PhD in Paris when he was working on the experiment Polar Bear. Then he moved a lot around Europe and the US, first to CISA, then back to Paris, then Brighton, the University of Sussex. Now he's a Marie Curie Global Fellow, joint between the Flatiron Institute, the Center for Computational Astrophysics in New York, and the Cardiff University. He worked on a wide range of topics, from CMB to large-scale structure, covering both theory and data. He's also involved in many experiments, so he's leading the CMB cross-correlation package in Science Working Group in Euclid and in the Simon Observatory. So he's a huge fan of CMB lensing. Yesterday, to quote him, he told us, large-scale structure is what you do while you wait for better CMB lensing data. And now he will tell us.
Quoting someone else.
Okay,
Thanks for the nice introduction. Today I'm going to talk about two sort of independent but connected topics. So my title is kind of broad and says Cosmology with all the new data, basically, and I hope it will be clear why new and why old at the end of the talk. So before setting the stage, I know that the audience has a quite broad range of expertise, so I will start with a short introduction. So according to the standard cosmological model that we have right now, the universe started in a very hot and dense phase that we call Big Bang. After that, it underwent a phase of accelerated expansion that we call inflation. During this time, the perturbation in density that later generated all the stars and structures and galaxies, so on and so forth, were formed. And as the universe expanded, it cooled down up to the point where electrons and protons combined. And essentially, the photons started propagating freely. That we detect these photons today as cosmic microwave background. But this also meant that the pressure that was sort of competing with the growth of structure is no longer there. And so structure starts forming. We start forming the first star. In hypothetical, we refer to as dark ages, let's say, and reionization. After that, the universe keeps expanding sort of linearly until recent time, where it started accelerating again, driven by what we call dark energy. And so this model accounts for a wide variety of observables, but we have lots of things that we don't understand. Dark energy, first of all, and I would say the other big mystery in terms of fundamental physics is the nature of inflation. So inflation is a paradigm. There are many theories that can account for this accelerated expansion. We would like to know more about that at some point. So if we have to solve this problem in cosmology, we can use several probes. I would say the main one in terms of sheer precision at present is the cosmic microwave background. You have here a summary of all the measurements down to basically 2020, I believe, and 2020. So you have the well-known CMB temperature and anisotropies with these famous wiggles. The information in this observable has been fully, I would say, exploited by Planck, and we got very explicit constraints on cosmological parameters, omega varying, omega n, a bit of dark energy, curvature, and the parameters that govern the details of the perturbation, so spectral index of the perturbation, the amplitude that we're running. The current generation of experiments that is starting right now, and the future ones, I would say, are essentially targeting the cosmic variance limited measurements of the polarization of this signal. You have two types of polarization, the E-modes that are also sourced by the main perturbation that generated the CMB temperature anisotropies. From very accurate measurements of this signal at very small scale, you can get lots of constraint on, I would say the same parameter, but affected by different kinds of systematics potentially, but also extra information about other stuff like the effective number of relativistic species in the universe. And of course, you have the famous B-modes of polarization, the other type of polarization that is generated mainly at small scale by the gravitational lensing of the E-modes. And this was first measured in 2013 by Polar Bear and Bicep, on this scale by Polar Bear. And then on the large scale, you have potentially the signature of the gravitational waves produced during the inflation that can create a signal, and this is still so far undetected, and it's the holy grail of the coming generation of experiments. On top of this, of course, you can also, so this signal, normally parameterized by this R parameter, can tell us a lot about the physics of the mechanisms that generate. And of course, you have other improvements on other parameters that you want to learn about, like the neutrino masses and so on and so forth. Now, if you are, however, interested in, I would say, dark energy science, CMB is helping, but not extremely, because CMB alone is weakly sensitive to the physics of dark energy, the detailed mechanism that drives the acceleration, I would say. So another, let's say, complementary way to learn about this, and also other parameters, is looking at galaxy surveys. One of the probes that you can extract from the last day structure is essentially looking at how the galaxy cluster as a function of scale. So you have this plot from this recent paper by Oliver Peacox, showing the matter power spectrum as a function of wave number, and from this you can learn lots of things. But I would say probably the most common probe so far is again the wiggles generated by the baryonic acoustic oscillation. But you also have other competing probes, fractional space distortion, voids, and so on and so forth. The detailed shape of this function here depends on parameters that govern the growth rate, and you have an example here that shows the effect of neutrino mass in these parameters. Yeah.
Is the green line, like, are the solid lines the theoretical prediction?
Yes, I think it's the best fit model for.
Because at the high K, it's not the green error bars.
Yeah, so I think here, like, they're doing like a full shape. This is, I think, the paper that did the full shape analysis of the power spectrum. But of course, at some point, you have to cut in scale where your modeling becomes unreliable because of nonlinear effects. Yeah. So last but not least, gravitational lensing. So essentially, we know that the shape of galaxies gets distorted when the light coming from these galaxies passes close to dark matter clump that basically starts correlating the shapes of the galaxies behind this dark matter clump. And if you measure this effect, you can reconstruct essentially the matter distribution weighted by some geometrical function. The advantage compared to, let's say, the clustering of galaxies is that this probe is unbiased. So it probes literally the true underlying matter distribution, and you don't have the problem of connecting the luminous matter to the dark matter underlying. So these are very challenging measurements, of course, because the shearing of the image, you start from an unlensed galaxies, you shear it a little bit, you convolve it with PSF, you pixelize your image, and you have some noise. So you have to basically go backward. And this is very hard, and so far, not many surveys have done that successfully, but we started doing the precision measurements of this effect with the last generation survey. You have an example here from the dark energy survey. And from the electricity map, you can again compute a power spectrum and do inference of cosmological parameters. These measurements are also challenging because they are also affected by systematics, potential multiplicative calibrations. This extra term here that you get when you compute the electricity power spectrum, that essentially describe the fact that the galaxies have an intrinsic shape themselves, and they can generate essentially a bias to your measurements that you need to account for. Okay. So last but not least, the CMB lensing. It's essentially, if you want, the same idea, but the light comes from the most distant source of light you have in the universe. So it crosses through all the dark matter in the universe, and it gets lensed by all the structure. So this is essentially the what we call the lensing weight or the lensing kernel. It's a function that tells you to which at which redshift the structure that lens your background line are, let's say, most effective. So CMB, the efficiency of this kernel for CMB peaks around redshift 2, but you can compute it as well also for, let's say, other galaxies, other lensing survey that use background galaxies, and you have this example here in orange. And you can see that this function here and the lensing kernel of the CMB, they overlap. So which means that you have different way to prove the dark matter distribution with complementary observables. So you can also correlate the lensing map that you can extract from measurements of the CMB anisotropies statistically with what you get with galaxy surveys. State of the art is these measurements of Planck that was also very recently updated by Julian Caron and collaborators with an improved, let's say, optimal technique. But that's basically the best that we have at present. Now, when you do cross-correlation, this is just a cartoon to introduce a bunch of ideas. But essentially what you get when you correlate the lensing of the CMB or with Browser-Lasky structure is a weighted, let's say, measurements of the matrix distribution. And the weight, of course, depends on which kind of observables you have. If you have, let's say, a standard galaxy survey, you have, let's say, the matrix distribution of your sources, of your galaxies multiplied by the bias that relates light to mass. This is the usual kernel of galaxy lensing that I've shown before. This is very cool because you can do, as I said, extract additional information, but also look for different statistics. An example of this is this DG statistics that is shown here. That is a measurement of the growth rate that essentially uses the fact that cross-correlating with CMB lensing, you can form statistics that are insensitive to the bias of the galaxies. So you can sort of minimize the problem of knowing the bias very well to constrain the growth rate. Or an example here is the possibility of constraining these multiplicative biases of the cosmic shear measurements from cross-correlation. This is an old idea that dates back to 2012, but essentially people have shown in forecasts that for deep survey that we look at galaxies at very high redshift, marginalizing these biases basically would be possible only through this cross-correlation with CMB lensing. So lots of interesting science. Just to have like some forecast for what we expect in the coming years from this, I show here a plot from this recent paper that we put out with Euclid through the Euclid consortium, where we basically show that you can improve a lot in terms of cosmological parameters for a wide variety of even non-standard cosmological model when you add this cross-correlation with CMB. And the way to interpret this plot is the following. So you can imagine the black line here to be the error you would have on this cosmological or nuisance parameters for galaxy surveys in black, if you just consider Euclid alone. And if you add essentially CMB and all the possible cross-correlation with all the surveys, you go down to this orange contour. So you can shrink essentially the error by quite a lot, factor of 2 or even more. And this is even more true if you start looking at more general model, moving from flat lambda CDM to, I don't know, flat W0, WA, and gamma parameter, where gamma is the growth rate for generalized modified gravity. So far, the cosmology improvement is not there, but the current generation of survey essentially showed that the cross-correlation is already good to marginalize our systematics, and with the next generation, we start getting a huge gain in cosmology as well. Blue, I think if you just add an extra just the CMB lensing power spectrum to the inference, but not the cross correlations. Okay. All right. Now, state of the art of the whole field, I would say, in terms of measuring growth rate and cosmological parameters from CMB and galaxy surveys. There's this recent plot of a recent paper that we put out, but essentially you can show that there is a tension, and there is a tension in particular in this parameter, SA, that is a combination of omega m and sigma 8, so the density and amplitude of the matter fluctuations. And this tension comes essentially comes mainly from the low redshift probes, from weak lensing, and these are in tension with what you get from these parameters inferred from CMB. Here you have the measurements of Planck and the same parameters for measurements that come from CMB lensing or other CMB experiments. And you can see that when you start looking at these plots over here that essentially are constraints from the weak lensing data, you see a systematic, say, shift compared to what you get. So is this a real tension? We don't really know, possibly. We need to take into account one important fact when you start looking at all these different probes, which is the fact that different probes probe different scale at different redshifts. And you have this very nice plot here from Preston et al. Paper 2023, that essentially show you which kind of scale you probe and at which redshift with all these different probes. So you have primary CMB that probes very high redshift on sort of kind of linear scale, CMB lensing that also probes like sort of semi-linear or semi-linear scales. And the lower in redshift you go with probes with lensing or galaxy clustering, you start entering the nonlinear regime where lots of, let's say, uncertainty related to the modeling show up. So if we want to really assess if this tension is real, we need to understand if it comes from nonlinear effects or if it comes from some modification of physics, then it should also show up at high redshift. So we want to probe like mildly nonlinear or not scales that are nonlinear at low redshift at higher redshift to check if this is actually true.
So the color scheme is your preference?
No, it's no.
Blue versus red.
I think here it's. I don't know the details, but I guess this is danger. I would say.
Right. No, maybe
This case,
Yeah. Yes. The box is. Yes, exactly. That's as it is. Okay, so in order to follow this reasoning, I'm going to talk about this recent work that we did, trying to measure, to provide some measurements at high redshift on sort of quasi-linear scales of the amplitude of the matter fluctuation. So for this, we used essentially this this quasar survey that comes from Gaia. So Gaia is a satellite from ESA that is dedicated to astrometry. So their main goal was measuring the position and velocity of stars and map their position in the galaxy. But as a byproduct, people realized that while the satellite scans the sky, you can also essentially observe tons of quasars. Okay. And so the collaboration put out this catalog at the end of 2022 that released 6.6 million quasar candidates. The catalog is very complete because you observe everything on the whole sky, but has low purity, and there are lots of stars that are disguised as quasars. So you need to be very careful if you want to use this for large scale structure. The cool thing about this catalog is that essentially you can get redshifts that are pretty accurate. Why? Because Gaia has a low resolution spectrometer that uses a prism. Actually, there are two of them. You have here the total band for the full photometry here in green, and the total band for the full prism, the blue and red. And so essentially, you can measure lines and deduce redshift. You have this as an example that comes from the ESA website. And you have this data that comes from space. So they're very clean, there is no atmosphere, and so on and so forth. So it's technically easier to characterize systematics. Now, however, as I said, like cleaning this catalog is very hard, and lots of work went into this before doing cosmology. The heavy lifting was done by my collaborator, Story Fisher, that essentially did this. So you can do a cross match of a subset of this catalog, of this quasar catalog that covers the full sky on the SDSS footprint, for which you have very high resolution spectroscopic observation. And for this, you also have labels for sources. You know which are the stars, you know which are the quasar, which are the external galaxies. And essentially, with some color cut using infrared band that come from AWISE, you can devise some series of optimal cut in color space to identify which are the stars and which are the quasars. And you can see that in the same color space for this Gaia catalog, you can identify clearly the outliers. The other thing that you can use is the parallactic motion. So quasars are very far and shouldn't move. So you can play the same game with the parallactic measurements of the satellite, and you can see that there are lots of outliers that can be removed. Essentially, these are all essentially stars that were misidentified. Redshift estimates also needs to be corrected because these spectra are low resolution and there are lots of interlopers, so extra stuff that mimics emission lines that are not really real. And so we had a good fraction of objects with a catastrophic redshift, let's say. The accuracy was not great, so I would say 10%. But after some work on this, we improved quite substantially. The redshift accuracy, you have the redshift of our quasar compared to the spectroscopic counterpart when we have a cross match. And we improve it basically to have like a 1% error, roughly, which is great. The redshift distribution of this quasar is peaks at 1.5, but has a tail at very high redshift, so it's quite unique. And essentially covers 70% of the sky with an effective volume of roughly 7 gigaparsec. So I think to date is the largest quasar sample out there with good redshift error that you can use for large scale structure. So it's kind of unique. Other thing I mentioned, so the cleaning of this, sorry, the systematics of this survey are not very much because you are in space. So essentially, we figure out a model to describe the selection function of these objects, just including additional, let's say, residual stellar contamination from the Gaia catalog of confirmed stars, depth extinction, and the scanning pattern of the satellite that you can see here. So these are pretty much the only effects that you need to account to get like a good completeness and for the survey. What this catalog can do for cosmology, I think it's summarized here. So in this plot, you have essentially the matter power spectrum. And here you have not the wave number, but the projected scale, angular scale of the sky. Different color means different redshift. And you have superposed here the canolinear scale at each redshift and a bunch of like other reference scale. These essentially are the angular scale that we used to do our analysis. So we did our analysis in 2D. We can do it in 3D because the redshift is good, but not good enough to be a full 3D analysis. So essentially, we are probing, again, quasi-linear scale at high redshift, which is what we do. The fact that we have this large scale coverage allows us also to do an independent measurements of both the density of the matter and the amplitude of the matter fluctuation that normally are degenerate in weak lensing survey, and in survey they do not have access on the to the larger scale due to the finite sky area. You can see this property here, where essentially you have some best fit model as a reference in red, and the blue is essentially what happens to this curve if you perturb the matter density, and in green what happens to if you perturb the matter fluctuation amplitude. So essentially, you can see that if you just have access to, let's say, the smaller scale, these effects are kind of degenerate, but if you have access to the larger scale, amplitude is kind of different from the matter because you start tilting things and you can get an independent measurements of both the parameters. Then, yeah, this was work done with Kate and David that also came very recently here. I would say the money plot is this one. So if you look at the plot that I showed before with S8, now the S8 that we infer from the Gaia catalog in autocorrelation and in cross-correlation with CMB lensing doesn't seem to have attention decline. And the advantage of this, as I mentioned before, is that the measurements is very clean. So we tested the robustness of this with a lot of systematics, and we saw no effect, no evidence of strong contamination. However, there was some potential contamination that we had to work out, and it's kind of important. So go a bit more into detail. So this is a list of tests that we did, that we don't have to look at all of them, but essentially we found out that if we split our catalog in two tomographic bins and look at the low redshift part versus the high redshift part, we did get a difference in the value, for example, of sigma 8, of the sigma 8 parameter. So the low redshift part is in perfect agreement with CMB, but then if you look at the high redshift, it was not, which is kind of going the opposite direction of all the other probes that we are looking at, right? Eventually, we found out that the problem was not present in our catalog, but it was coming from the CMB lensing map that we were using to cross-correlate. And essentially, in this plot here, you can see, let's say, what happens to your data point if you cross-correlate with the fiducial Planck map in solid, or with a lensing map reconstructed only from polarization data in dashed blue. Okay. Polarization data of the CMB can be used to extract CMB lensing map, but have very different foreground contamination. And in particular, the CIB, the cosmic infrared background, so the unresolved emission of star-forming galaxies, is a very dangerous emission, very hard to clean. And we believe that it's responsible for this shift, so which is something that it was known for the CMB lensing auto power spectrum analysis. But now that we are correlating with these objects that overlap in redshift with the peak of the CIB emission, we are more sensitive to this effect. So once we use this polarization data, we go back to perfect agreement plan, essentially. The other downside of this, however, is that polarization data of Planck are very noisy. So you lose a bit in terms of your signal to noise, but you gain in robustness to foreground contamination. And I think this was the first time it was kind of shown, but in a way, the future is bright because the next generation experiment will improve a lot on the polarization part. So we can expect that deep data that comes from space, for example, for Euclid, if you have to use them for cross-correlation, will not suffer from the same problem, thanks to the fact that polarization data will be more sensitive.
So here, at the low angular multiple,
yes.
the measurement, I mean, it looks like you cut it out.
Yes.
The low angular measurement, angular multiple measurement is low, but on the other hand, in the previous slides, the Poita auto was higher.
I think so I will get back to this because it's basically what I've been working on recently. We will be working on recently besides just the scales. But no, so I think the do I have this one?
One for the back.
One for the back.
Yeah, here it's high.
Yes, but this is the yes. So when you look at the autocorrelation, the systematics, they add power all the time, most of the time. While this is
More like
no, it's a bit on scale dependent, but I think the answer to your question is this is the autocorrelation. And if you have, let's say, you can imagine that if you have some additional components, say additional stars that are not removed, they will add power in the autocorrelation. But when you do the cross correlation, it doesn't correlate with the external tracer. So you don't see this excess in the cross correlation, which is one benefit of this.
But then
Now it's a bit low, yeah. Yes. All right. So to get a bit into more details on additional things we're looking at, let me zoom a bit on inflation and why this is important and what we can do with PIA for this. So in the standard model of inflation, essentially you have that at some point in the history of the universe, the energy density was dominated by some sort of potential energy slowly rolling down to reach an equilibrium. And this essentially, slow rolling drove the exponential expansion. However, if you constrain the amplitude and tilt and the spectral index of the primordial perturbation that eventually evolve into CMB and LSS structure and so on, you can get an information on the shape of this. Okay, so we know quite a bit of things about this potential, but a complement, we don't constrain everything. And one potential way to get more knowledge on this mechanism is looking at primordial non-Gaussianity. That schematically, any some-specific class that are the local parameterization can be written like this, and essentially they describe how eventually this scalar field couples, let's say, to anything else out there in the universe, potentially different fields or that can or cannot interact, and so on and so forth. So if you constrain this parameter FNL, you can get additional constraints on the physics of inflation. And you can do this, of course, looking at the CMB. The best constraints come from the CMB measurements. But you can also look for it in the LSS structure data. And in particular, I would say this is known since the early 2000s, that non-Gaussianity introduced a scale-dependent correction to the bias of the galaxies. So when you look at the bias of the galaxies, you will not only have an effect that depends on redshift, but also on the scale that you're looking at. So for, let's say, a positive value of FNL, this is a cross-correlation between the halos and the matter. You will get an enhanced power spectrum. For a negative value, you will get a suppressed power spectrum. And if you want to prove this kind of effects, because they go as 1/k, you have to look at the very large scales. And to do that, you need to have survey that cover a very large volume or a large sky fraction. And you also, if you want to enhance the effect, you want to have tracers that are highly biased. And quasars are perfect for this. They answer to all these requirements. So essentially, we started looking at the analysis of the FNL with quaya. So here you have an example of how good these quaya data are on the larger scale. And so I'm showing on the left the autocorrelation of the quasar that come from the EBOS survey, which is, I would say, the state-of-the-art spectroscopic data until the DAISY comes out. And I project them on the sky, I compute the power spectrum, I get these points here. And in solid black, you sort of have the expected signal from, let's say, knowing the bias and the Redshift distribution of this quasar. And so all this excess comes from systematics. And of course, like people, this is a bit, I'm not arguing that people have done cosmology with this, but they work a lot to reduce this with various techniques. Now, if I do the same thing with the quaya quasar that are space-based, I get this. Okay, this is not a fit, it's like an expectation. And so you can see how different the level of systematics is, and all this excess that you see at the larger scale is much lower, even without any systematic screening, compared to the ground-based data.
But they are not the same sample.
They're not the same sample, but basically the discrepancy would be between point and theory. And so you have like a couple of orders of magnitude. Here it's much less than this. So we did some forecasts analyzing this autocorrelation and the cross-correlation with CMB lensing, and we expected to get an error on FNL of about 18, which is essentially competitive with any 3D measurements that was recently put out. So we were kind of excited about this. Okay, yeah, so I will get back to this in a sec, but basically the constraining power comes mainly from the cross-correlation. I said, like, with the CMB lens in kappa, because the shot noise is very. This is the shot noise. So some preliminary results that we've been working on. Kappa G measurements, very noisy. So this is essentially an almost multiple by multiple analysis with maximum likelihood power spectrum estimator that are numerically expensive but very accurate. And you have a curve with FNL equals 0. And here you have the same thing for the autocorrelation. And you can see that for the first few multiples, we still have to get rid of them because there is still a big excess due to systematics that at present we did not manage to remove. But this basically affects only the first 15 multiples, and after that the measurements is clean. By clean, I mean that these data points are robust to any systematic subtraction that you can try, or at least that we tried so far. So preliminary posterior is here. Sadly, we are a bit off compared to a Fisher forecast. The error we get on FNL is 30. And this is precisely due to the extra variance that these systematics add in the measurements. So we're still working to improve it, but still I think we are essentially having the best constraint from this kind of technique to date. Yeah, sure.
Here, are you measuring FNL or the combination of FNL with phi?
Technically, is FNL with phi. Yes. Yes. All right. Are there any other questions for this? Okay. If not, I will try to jump to an orthogonal. So this is work in progress, but we hope to finalize this by, let's say, the end of the year or so. All right. So now I'm going to switch gear very briefly in the last 10 minutes or so. Showing a different way that we can use to probe primordial non-Gaussianity. Okay. Now, as I said before, like each probe probes different scales, and non-Gaussianity that we probe with Lasky structure and CMB are on relatively large scale. But what if we want to probe non-Gaussianity at different scales? So one way to do that is, I'm going to do a little spoiler, is using CMB, but in a different way. So very often we talk about the CMB just in terms of anisotropies. Okay. But the CMB has much more information that, in a way, is kind of forgotten. But the spectral energy distribution of the CMB also contains lots of physical information on the physics of the universe. And now, to cut this in short, so if you look at high enough in redshift of above 2 × 10⁶, there was perfect thermal equilibrium in the primordial universe through quantum scattering, double quantum scattering, and a series of reactions. But as the universe expands, it cools down. So at some point, we reach a point where reactions that create photons are not anymore efficient. And so the number of photons is frozen. And if you have any extra creation of photons from particle decays or anything like that, you will distort the perfect black body shape of the CMB. And we call these effects mu distortions. Now, you can also reach a point where quantum scattering becomes kind of inefficient. So if you have any energy release in the plasma, it doesn't get thermalized and creates another type of distortion called the Y distortion. And it looks like this. These are variations compared to the black body. And this is sort of known because at low redshift, we use it to detect galaxy clusters through the Z effect, for example. But you have a component that comes from reionization, technically. The bubbles that reonize the plasma can also introduce this kind of things. So there's lots of things that we can learn. Oops, I'm going backwards, sorry. You can also probe primordial non-Gaussianity with this. And how? Because essentially, if you have your CMB power spectrum in mind, you know that the power goes down as a function of scale because of the damping. And the damping of these acoustic waves also releases some energy in the plasma that can generate a mu or Y distortion. And because they come from density perturbation, you can also write down a model that essentially couples temperature fluctuations or polarization fluctuations with distortion induced by the damping of the acoustic waves. And this was figured out, I would say, in papers, I'm quoting this, but there are others, of course. And essentially, if you correlate, say, a map of the mu distortion with temperature or EMOS polarization, CMB, you end up probing very squeezed configurations of the primordial number sequence. And because mu distortion appear as a quadratic coupling perturbation, and you have one large-scale mode that comes from CMB. So essentially, if you measure this, you have the amplitude of this signal depends on the average mu distortion in the universe times FNL, and you end up probing non-Gaussianity at super low small scale, like from, I don't know, 50 to 10,000. And similar for Y, but because it happens at a slightly lower redshift, you probe like more, let's say, linear things. All right. Going very fast, but not too fast. We only had one measurement that tried to fit this, okay? And this measurement was done by the FIRAS instrument that I don't know if people are familiar with, but basically it was the reason why the Nobel Prize in Physics 2006 was given for the measurements of this function here and for the first detection of isotropies. This is the most perfect black body measurement, black body spectrum you can ever have. Yeah, the famous plot was like, this is 400 times the error paths, just to make them appear on the plot. But after these measurements, nothing was really done till now, apart from some attempt to extend these measurements to the ultra low frequency by Arcade and TRIS. But essentially the upper limit on the amplitude of this spectral distortion are still the one that comes from FIRAS. So, okay, let me skip through this, but basically, if you improve these measurements, you can learn a lot of things. For example, a dark matter model that decay in the early universe, and you can constrain like the mass of this particle or the energy injection scale, or so on and so forth, many things. I'm going to skip to this a little bit because it's technical, but essentially, because we are not expected to, despite people have tried to propose missions to upgrade these measurements, nothing is there on the horizon. So at some point, Federico, my collaborator, Federico Bianchini, and I thought, why don't we go back to this data that was taken 30 years ago and try to reanalyze them with modern technique, okay? And if you think about CMB and you've seen the Planck maps, there are basically 10 frequency bands. And you can essentially think about this data as a cube with 170 frequencies that go from 60 to 3 terahertz. And the sky essentially changes quite a lot, right? And it's kind of unique data set, right? So essentially what we did was improving one crucial aspect of this analysis that was not very known at the time, which was essentially cleaning the foreground emission from the data. And the main concept is this. So you have your CMB that looks like a black body here, and you have other emissions that emit with different emission law. And if you have multi-frequency observation, you can essentially fit for this model and fit for the sky model and separate all the components. And this, you have an example with Planck that has 9 frequency, but we have now 170. So we should be able to do this process much better. Sorry. A quick thing. Essentially, I'm gonna go quickly to this and then show you the results. But basically, what people, of course, people knew this problem before, but they didn't really know how to do it super accurately because there were no data or no ideas people did. So essentially, they fitted their sky model as like a black body plus some boost, some dipole due to the motion of the satellite. Sorry, due to the motion of the solar system with respect to the perimeter CMB, plus some foreground template, and they fit it for an amplitude. Okay? But this foreground template came from their own data, because there were no other data. And then they took this function here that was supposed to be the black body and fit for distortion, okay? Linearizing this with some residual template of foregrounds. So it was a bit of a convoluted process, but we thought to do it better because essentially for each sky pixel you have 170 frequency measurements in frequency, and you can do this component separation in a Bayesian way, fitting a model with full Monte Carlo techniques that were not available at the time. You can get the full posterior, and so on and so forth. So we did this exercise and essentially came up with for each sky pixel with a value of mu marginalized over a bunch of different focal models. So this is a map of mu. Looks like noise. The noise is very high. But we did go through the full process of correlating it with the E-node of polarization and the temperature. Okay. The spectrum looks consistent with 0. On top, you have MOX just with noise, just to check that it basically looks like noise. We don't detect any signal. But we can get some constraint on Gaussianity. And so you have here essentially an attempt that people tried using Planck data that we found out it was wrong. Like there were some faults in their analysis. And we reanalyzed this, and basically we got this gray posterior from Planck data. And the final posterior for us, it's here in red. Okay. Look at the scale, right? This is like super high, but it's completely comparative, like completely, let's say, different scales. And actually, like if you measure the amplitude of FNL at this scale, you can also constrain a bunch of other models that predict that the non-Gaussianity changes as a function of scale.
Sorry, what? 6?
Say again, sorry.
What?
This is the value of FNL times 10 to the 6.
Oh, so you're constraining 5 times 10 to 6?
Yes, but at scale of 10,000.
Oh, okay, that's right.
Yeah, right. So this was the first measurements that was done like this. And we also showed that actually instruments like FIRAS are subjected to a different set of systematics. And actually, if you use instruments like Planck to do this analysis, you have to account for a bunch of other astrophysical effects that were neglected. So the true posterior you would get from Planck is this dashed graph. So much less constraining in reality than the FIRAS data. Okay. And essentially, I can chat a bit more about the systematics if you're interested, but it's definitely a bit technical. But the takeaway message is that future CMB experiments can do this kind of analysis and doing it much better. So the error we expect from the next generation surveys from this kind of techniques is 1,000, not 10 to the 6, so 1,000 times better. Yeah.
I think just to get picture for me, FNL, so FNL is the parameter which is telling you if it's non-zero and there is a beyond inflation theory. Or...
Well, at least there are different mechanisms then. So standard single field deflection predict that this FNL value is close to 0, very low. Like if you detect something, then depends, which type of configuration you're looking at, but you can learn about if there are multiple fields or how these multiple fields can interact and so on and so forth.
So when you're reporting the results, why are you only reporting variance, not also the mean value?
What do you mean?
So like
Close to the non-detection.
It's a non-detection, right?
So it's just
Yes. Consistent with 0, yes.
But what is the assignment of those three? What's the improvement to get better?
We didn't do the forecast, but it shouldn't be too far from this, like probably a few times worse.
No, but it's a small scale, more precise small scale.
Yes. But the crucial thing here is that if you want to have a constraint that is model independent, you need to measure the average of the moon. And this you would only get it mainly from a spectrometer, not from a standard CMB experiment.
Right. This one is you need accurate.
Yeah, so we use the temperature because the copy temperature is very noisy, right? But we could get a better moon.
Do they have a spectrum?
No, it's gonna be like Planck, like several bands, yes. So, but you know, if you look at the anisotropic part, is good enough. But the total signal, the amplitude depends by this. So you need a way to measure the absolute scale. Right. And this is only doable with a spectrometer.
Right. So CMB S4
yes.
will not improve anything.
No, we'll improve. Well, we will be limited by the fact that we don't know this.
Right.
But if we're just looking at the anisotropic part per se, if we assume that we're not going to improve the moon, that's, however, the final error. All right, so I'm kind of, I will wrap up. Okay. All right. So last cool thing, we did improve actually on the monopole of the moon by a factor of 2. So from the 90, that was the original measurement of 5, we went down to 50. This was also cool. So we skip this, but we also, just to show you just this plot, kind of busy. We did also improve on the average of the Y distortion, not only the mu distortion. And we basically realized that with these new measurements we got, that we can ask about later, we start constraining some models of galaxy formation. So as I said, we detect clusters through the SZ, and if you can take the average of all the possible clusters, you will get a measurement that depends on the cluster physics and the physics of the gas. And for the first time, we were able to place some constraints on galaxy formation model from this. This is work in preparation that I will not have time to talk about, and I will leave you with my conclusion here. Happy to answer questions.
Question for Giulio?
It's really nice to see how you give another life to these data sets that are either old or meant to do other stuff.
It was my vintage project.
I was wondering if you could give us more details on why Paris is that unique. Like basically the slide you skip.
This one.
Why this experiment is like still unique?
So basically, okay. So this is the schematics of fire. So you have the sky, okay, that goes to, it's an interferometer. And so you acquire some measurements on the sky, then you have a beam splitter, you have 2 wide frequency bands, and a movable mirror, essentially, that, depending on the position, the optical path changes. And essentially, you compare this to a reference that you know very well. And essentially, you have a measurement that is absolutely calibrated. Okay. Absolute in a sense that depends on how well you know your reference.
The reference is some kind of...
It's a black body that people know, that people have there. They know to, I think, 0.5 millikelvin error.
So they brought this also in the satellite. It's there.
It's there. It's on space. Okay. While Planck doesn't work like this. It doesn't have a reference. So essentially, how they do it when they calibrate, so Planck is much better to measure fluctuations, okay, compared to fires. But this essentially, Planck essentially uses the fact that the satellite moves and creates a dipole in the CMB that it observes to calibrate, because you have, let's say, the cosmological part, so the solar system that moves compared to the CMB, but you also have a dipole induced by the satellite because the satellite itself is moving, and you know the position of the satellite to basically 0 error, okay? And so you can use this modulation of the dipole induced by the satellite to calibrate. But to do this, you need to assume the temperature of the CMB, and the only measurements we got was from these guys. So that's a bit the technicalities.
While we're on topic, so well, I mean, you said like you said, CMB is like the ultimate black body. But then we're using something it's an IP. Then we're using its reference into black body. I mean, how can we get something better than the thing we use calendar?
So the initial measurements of it's definitely not okay.
What?
The initial measurements that they put out from the virus, it's not the final error you see quoted, right? Which is like 0.58 millikelvin, I think. So, but basically, I think they had different ways to estimate this, and one way is looking at the broadening of some emission line in the galaxies, Doppler effects. But the ultimate thing that people did was basically using the dipole, okay, from WMAP that is known basically to zero error, okay, and then they put it back into this data model here, okay, and they look at because this is known with zero error. This doesn't really matter, it's a constant offset. And then instead of looking at the black body, they look at the amplitude of the dipole, so the derivative of the black body. And that also depends on temperature. So that super mini error comes from this. So not many people know, but otherwise the error on the monopole, so the error on the black body itself comes from the calibrator.
Okay.
Yeah.
Any other question?
Got one more. So can you show the new map?
Yeah.
So here you're saying you're doing new measurement each pixel. You have 170 frequency, and so you get new in each pixel.
Yeah.
But
you're fitting it jointly, right? New is same in each frequency.
No. So for each position, basically we have a measurement like this. For each sky, the data is like this. So for each sky positions, ski pixel, you have a spectrum. And you can fit a sky model just for that spectrum.
Okay.
But in the end, it's a virus measurement, so that angular resolution, I believe, was very.
It's 7 degree.
Looks like your SkyMap, or mu SkyMap is a very high resolution.
No, it's in total 3,000 pixels over the whole sky. No, it's yes, just 3,000 pixels. Very noisy, just 3,000. I mean, less we get rid of some of the galaxies.
I have a question, and it's not fully well posed, but we had a talk 2 days ago by Subhi Sarkar.
Yeah.
And was talking about how lambda CDM could also have this assumption that wherever we are not special and everywhere we should see the same thing.
Yeah.
But I think these things may work in CMB, which is just very early universe cosmology, but may not work in late stage cosmology. Could this be one of the reasons of our attention in this?
To quote Jim Peebles, I think in his Nobel Prize speech, he said that this dipole problem that we see, I mean, we have to understand if it's like the large-scale structure, the same problem, right? The same dipole, sorry. And some attempts didn't really work out. So some people claim there is some tension. There was some recent work done by the JPL group showing that if you do the analysis statistically right, accounting for the effect of local motion and the fact that you don't know the redshift of the survey of the objects that people have used to do this, that are mainly radio galaxies, you don't have attention. And we are trying to do the same thing with Quaya, but I cannot really say so far. But there is we have to measure, right? And I think so far, I think the evidence that people have claimed so far are not very convincing statistically, if you do things properly. But, I mean, face value, yes, you have this problem.
Yeah.
Now it's a method, quoting the significance, then goes back to statistics, and now you account of the errors, and people have argued that, especially these radio galaxy things, the measurements are not very conclusive. Like there is no tension. But we see, like, I think like Euclid would do it. You need like very large scales, right? So the space is the perfect thing. So people will do it with Euclid. We're gonna do it with Quaya. You know, everything will be done at some point.
From that talk, if I remember correctly, you were already saying you can only see 1/3 of the sky. So
I mean, yeah, sure, but at some point, you know, if it becomes a bit philosophical, right?
Yeah.
So you wanna make a claim, you do a measurement. Like if the measurement is inconclusive, then you don't support your claim.
Thanks, Giulio, again.
Thanks. And thanks for people on Zoom.